For this project, my wife was the customer. She asked for a dimmable night light with a temperature display, so we could check up on our newborn at night. I've been wanting to use a 555 timer in one of my projects and thought that dimming the lights would work great using PWM signals outputted by the timer. So after sitting down with her to understand exactly what she wanted, I got to work. I'll go over the different parts of my final design, I'll go over some of the mistakes I made and how I fixed them, and then we'll see how it all came together. Let's start with the electrical schematic. I'll shortly go over each part. Okay, here I put some header pins for the display, since it's not soldered directly on the board. Here is an IC socket for an ATtiny85, which will read the temperature sensor data and display it on the LED display. Next, we have the temperature sensor. And here we have the voltage regulator, which is completely unnecessary. I confused the ATtiny85 I/O pins with the Raspberry Pis, which can handle a maximum of 3.3 volts. However, the ATtiny I/O pins can handle 5 volts, so this was a non-issue. Next is the USB Type-C port used for the 5-volt power supply. Now let's get to the PWM circuit. On the left, I have 4 pairs of LEDs connected in parallel. I calculated the required resistor size to limit the current on the LEDs. However, initially, I didn't use a resistor and limited the power on the LEDs using the PWM alone. I did this after seeing GreatScott's video on the topic, where he mentioned it's possible to control the LED intensity with voltage control alone, without using a resistor. I'll put the link in the description. That didn't work so well and caused the LEDs to flicker. After seeing the flickering, I added the resistor, which fixed the problem. On the right, I'm using the 555 timer to output PWM signals to the transistor. I'll leave a link in the description of a great video which details the use of 555 timers for PWM outputs and how to use a potentiometer to change the duty cycle. Here are the most important equations you'll need, which I got from that video. I noticed that when I turned the potentiometer to its maximum, the PWM duty cycle was way too high for me. So I simply added a resistor to the discharging side, which increased the off time, so it reduced the maximal duty cycle. I switched between a few resistor values until I reached the right value for me at 80,000 ohms. Now I want to go over the switching on of this system. One of the requirements my wife gave me was that she wanted the potentiometer to also turn the system on and off. She didn't want an extra switch for that. So after finally finding a potentiometer with a switch, because they're apparently not that easy to find, I noticed that the power rating of the potentiometer was very low, so I thought I wouldn't be able to power the entire system through the switch. That's why I designed the following circuit. Once the switch is conducting, there will be 5 volts at the MOSFET gate, which will cause the MOSFET to conduct, which will connect the 5 volts from the USB to the VCC. Great! And it completely didn't work. It took me a while of debugging and staring at the circuit before I realized the huge mistake. I saw a friend make the same mistake, so I thought I'll take the time to explain it. The voltage at the MOSFET gate isn't what matters. What matters is the voltage difference between the gate and the source. Once the switch is turned on, the voltage at the gate rises together with the voltage at the source. The higher the voltage at the gate is, the more current can flow through the MOSFET, which results in a higher voltage drop on the resistor, which means a higher voltage at the source. This limits the voltage difference between the gate and the source to a certain value. This results in potentially a lot of voltage dropping on the transistor itself. MOSFETs are usually used in their saturated state, meaning the voltage difference between the gate and the source is high enough to pass the desired current from the drain to the source. Not in this in-between state I implemented, where the MOSFET didn't behave as expected. For this use, a P-channel MOSFET, which works in reverse to an N-channel MOSFET, could have worked, but I didn't have one lying around. After showing this mistake to a friend at work, he asked why I didn't just connect the 5 volts to VCC directly through the switch. I told him that the switch can withstand very low power. And after he said that doesn't make any sense, we looked at the datasheet and yep, I just read the datasheet wrongly. It can stand way more than I thought, and that's when I moved to this much simpler connection, which works great. Here's the layout. I did this on a 2-layer board, and what remained was putting it all together so my wife would actually want to use it. This is where my friend Barak came into the picture. He designed and 3D printed the lamp as a present for our daughter. Here's what he modeled, which we really liked. And here's the printing process. I'll leave a link to his website in the description if you want to check out his other work. It came out better than I expected, and my wife is actually using it, which means it's not half bad. Alright, that's it for this video. Thanks for watching, and see you next time.